For my Sundial project, I've decided to take a slightly unconventional approach by programming a rather simple software that can calculate the time. Firstly, a conventional sundial functions because the angle of the sun in the sky, alpha and beta in this diagram, is relative to the time. To represent this relationship, I've measured a few points and plotted them onto a graph. As you can see, each value of angle of the sun in the sky have two intersections with the curve, which gives us the AM time and the PM time. In practice, if the angle of the sun in the sky is required, the time can be calculated by solving the quadratic equation of the curve. Acquiring the position of the sun in the sky is split into two parts: obtaining the frame using the webcam and process that frame to find the angle of the sun. I've used OpenCV and NumPy to help me with processing the images, as they are very time efficient. Taking the image is made very simple with OpenCV, the image.read method. And then to find the sun in the sky, I've created a simple but rather effective algorithm. Firstly, each tuple, which represents the RGB values of the pixel, is summed. The output value suggests the brightness of the pixel. Then, using numpy.where, all the brightest pixels of the image are selected. In the screenshot of the program to the right, the selected pixels are colored orange. Now, to find the sun, simply find the average position of all the selected pixels. The algorithm is quite effective because, as shown in this screenshot, despite the circular shape of the sun is disrupted by the trees and the sun itself is hidden behind the clouds, the estimated position of the sun is scarcely affected. An advantage of my program compared to a physical sundial is that I can correct my calculated time to the equation of time, because in reality, the movement of the sun in the sky throughout the year is not a constant. In fact, it can vary up to 40 minutes with the average time. This is due to the elliptical orbit of the Earth and the tilt of the Earth. At each stage of the year, the difference between the time observed, the apparent solar time, and the average times throughout the year, the mean solar time, is represented by this graph. In the runtime window, a live video stream is accompanied by the apparent solar time, the mean solar time, the angle of the sun in the sky, the refresh rate, a hint of where the horizon should be aligned, and the estimated position of the sun. There's also a trackbar on the top of the screen, which allows the user to input the current month, so the program is able to correct the apparent solar time to the equation of time. On average, the stream can be outputted at more than 10 frames per second on my Surface Book, which can give an impression of a continuous stream.